me a great pleasure to welcome Stanley. Now, I first met Stanley when he was a recently finished PhD student at the University of Florida with Shiva Ramakrishnan Balachandar, which we usually call Bala. Professor Bala was studying many things in multiphase flow, avalanches, particle-laden flows. So Stanley worked on shock waves with particles, and Bala certified me that Stanley was exactly what I needed to study atomization. So we hired him as a postdoc, and then Jose Maria also hired Stanley as a postdoc, right? So he worked for 3 years at D'Alembert on many aspects. It was a very bold move because then he returned to the US, so it was his intent all the way. So he then got a job at Baylor College or Baylor University. I'm never sure whether it's college or university, which has a very strong school of medicine. And so he started the studies of multiphase flow with his own group there at Baylor. He hosted a number of people from Sorbonne University, including master students at Baylor. And very recently has moved to the University of Southern California, which is Department of Medical Engineering, where he's now. And he's going to talk to us about aerodynamic breakup of vaporizing microdrops. And that's a new topic, so I've never heard about, so I look forward to it.
Okay, thank you very much. It's such a pleasure to be back to D'Alembert. I finished my postdoc 2017, so time flies. It's 7, 8 years past already. But when I came back to visit, look out the window, it's just like yesterday. It's definitely a pleasure to be back here. And today I'm going to talk about. Okay, let's see. It was working. Oh, okay. So I decided to talk about a topic that our group have been recently working on. It's aerodynamic breakup for droplets, and more specific, we'll look at micro droplets. It's not the typical millimeter-sized droplets, small droplets. And you know, when small droplets happen, they have a high surface to volume ratio and have strong vaporization happen as well. And how will the vaporization characterized by the Stefan number, and also when the drop size reduced from millimeter to micro droplets, the Reynolds number will change, and how will this change the dynamics? As Stefan mentioned, now in University of South Carolina, and there is a 6-hour difference between South Carolina and here. So it's 5 a.m. in the morning. So right now in my home. So if you see that I don't know what I'm talking about, that's a jet lag. So this outline of my talk today, I want to first give the background, why we want to work on this problem and why aerobreakup is important. And then I start to look at one of the topic at a time. First, I want to talk about micro droplets. What's the effect of Reynolds number on the breakup dynamics? And then I move on to talk about the vaporization, the second topic, and the effect of Stefan number. And the third topic is if we will be able to do high-fidelity simulation, you get regular simulation data, but it's so expensive. How you can use those data, develop a model that people can use to do millions, billions droplets. And that's some of the machine learning work we have been recently doing. And at the end, I will summarize in what future work we're trying to do. So definitely you can tell I have been a postdoc in this lab and started to get interested into interfacial multiphase flow. We're interested in develop numerical methods, use the method to understand the fundamental multiphase flow thesis, and then if you understand the thesis, how you can improve flow control technique, field injection, and so on. So some ongoing projects in my group, we are working on a bubble migration in microgravity environment. If there's no gravity to rise up the bubble, you have a channel that has a wedge, and the capillary force can drive the bubble to move away from the narrow channel, the narrow region to the wide region. We also look at some cases high-speed flow. You have the shock wave and droplet interaction. Also look at turbulence and atomization, and also some like a new configuration from atomization called flow-burn atomization, and also we're interested in oscillation of a sexual drop with a dynamic contact line, dynamic contact angle, and of course the topic I'm going to talk more today is you have a drop, aerodynamic breakup of it. So this will be the focus of my talk today. So I have a couple postdoc and a couple PhD students working on this, and we only work on the simulation side. So I also collaborate with some people focused on experiment like Isaac and Jacob, and also my colleague in South Carolina, they work on modeling, Yuang. So these are the collaborators. So I mean, as I show in this video here, if you have a droplet, you suddenly exposed to a free stream with a high velocity, the gas inertia will translate, the energy will translate to the surface energy of the droplet. If it's so large that the droplet cannot handle, they will break. And this is what we call aerodynamic breakup. Okay, so through aerodynamic interaction with the flow, you can break. And why this is important, if you look at fuel injection, liquid fuel injection in an engine, so those liquid fuel injected and they will break into small droplets. And even you sneeze, I mean, the liquid out from your mouth also going to break into small droplets. And there's also some applications of high-speed fly hit into a rain cloud or just a cloud of droplets. You can have the interaction between the droplet and the flow around the vehicle can also introduce aerodynamic breakup. So this is just one of the few applications that why people care about aerodynamic breakup. To look at the fundamental physics, we typically simplify the problem in a way that we look at only a single droplet, initially stationary, with the diameter, density, viscosity, and surface tension exposed to a uniform stream with the density of viscosity of the gas and velocity. Okay, so if you do a simple dimension analysis, we find out that there's only 4 dimensional parameters: the Weber number, the Ohnesorge number, the viscosity ratio, and density ratio. Okay, so sometimes I love to look at what the meaning of these dimensional parameters in terms of ratio of time scale. If you look at the velocity, the time scale of deformation of the droplet is the convection time scale. Combined with the density ratio is what typically people use to characterize the droplet deformation time, and the capillary time and the viscous time. If you look at the ratio of this time, the ratio of the surface, the capillary time and the viscous time scale gives you Ohnesorge number, and the capillary time by the deformation time gives you the Weber number. So if Ohnesorge number is very small, that means, like a lot of cases people study, the millimeter water droplets, the Ohnesorge number is quite small, just because the capillary time is so much smaller than the viscous time scale. So viscosity is less important compared to surface tension to stabilize the drop deformation. And typically, then that's why people use a Weber number to characterize different breakup modes. So if you're bigger than a critical Weber number, for the millimeter water droplet is about 11, 12, your drop will start to break in the back mode. If you keep increasing the Weber number, you include a back stem, you have a back, have a stem at the center, or you have multiple backs, and even the shear breakup. And that's has been shown in many experiments. This is one of the more recent one that they have high quality images show the details, morphology of the drop. Okay, so a lot of works have been done for millimeter droplets. Okay, and that's understandable. If you're in the lab, want to do experiment, the millimeter drop is still reasonably easy to capture and look at the shape and so on. But actually, in a lot of applications, there are some micro droplets there that they may break or not. But quite often we ignore that. We think that, oh, it's so tiny, so small, the Weber number is automatically small enough, if breakup will just not happen. Just treat it as a sphere, that's enough. But that's not the truth. I mean, if you can understand that if the relative velocity is high enough, the Weber number is reasonably large, they will still break, right? But if, let's say, I can drive a velocity, relative velocity on a droplet, it will break. How will the drop size influence breakup dynamics? Okay, if you fix the Weber number and change the diameter, you easily prove that the Reynolds number will decrease of the diameter of the droplet. Okay, so if let's say my Weber number is 12, I have a 1 millimeter drop to a 10 micron drop, you'll find out the Reynolds number decrease order of magnitude. Does that matter? Okay, and another effect is that the ratio between the physical cutoff length, right? We know that if a liquid sheet is smaller than 100 nanometers, the disjoining pressure will start to collapse the liquid sheet and forming holes inside, right? If you have a millimeter drop, you think about that, the liquid sheet need to go to 10 nanometers for the holes to form, then you spend like a 5 order magnitudes. But now if I'm talking about 10 micron drops, that ratio might become much smaller. So the bag will not necessarily get a chance to form such a big bag before they break, if you look at the micron drop. These are the drop size effect. Another thing is that, like, interested in general in fuel injection, right? So the engine is hot. So if the ambient temperature is high, you have vaporization happen at the same time when the drop deforming and break. How will the vaporization influence the drop breakup dynamics? Right. I mean, if you use the Stefan number, that is the ambient temperature minus my droplet temperature, that will characterize the strength of the vaporization. If I tune that knob, how will the breakup dynamics change? So those are the kind of questions we want to answer. And there's some previous studies, but still a lot of gaps that we find out that we get a chance to fill. So we use the Basilisk solver. Yeah, hooray. Right, so I don't think I need to talk too much about that. Probably the only contribution we have made is we add our module for the phase change so that we can do vaporization. I will briefly talk about that method. It's a small extension, but this is a great code. I mean, use AMR, we can scale it, and you can see some of these simulations with thousands of CPU cores and run quite efficiently on a supercomputer. So as I said, we have the simulation data for a single droplet, but I know in reality is that, well, this is something that when I was still here, started to simulate, right? Atomization, right? There are many of droplets over there, right? So if I want to do also the level of refinement to a single droplet, and I want to do a simulation like that, here I use 2,000 cores. I don't know how many cores I will need to use over there. Okay, so there's a need that we can learn from what we do on a single droplet and subtract the phases over the data somehow in a subgroup model that people can use to simulate a large number of spray. If we cannot do the atomization part, at least in the downstream dispersion part, we probably do not want to use WRF to resolve all the interface. That's kind of the motivation. And if you do not want to resolve the interface, resolve the flow around the droplet, then you suddenly find out a lot of things you need to model. You need to capture the drop deformation, and you look at the literature for the so-called Lagrangian spray models. They have a lot of models, the TAB model, the Helmholtz-Rayleigh-Taylor models, and some internal flow model by Villamot and some other people connected to the standard, but none of them really capture the whole story. Okay, and now you don't resolve the flow around the droplet. You need to know the jack, and you know how to move the droplet. And also, if you have phase change happen, you need to be able to predict how the vaporization rate on the droplet. Okay, when you don't resolve the temperature field around it, and how do you model that? For quite a long time, people just assume the small, tiny drops are spherical, and all those vaporization models based on spherical drop. And if a drop deformable, right, oscillating in shape, how will the vaporization rate change? And those kind of questions have not been studied until very recent years. And I believe we're in a much better position to attack those problems nowadays. Okay, so in general, after long introduction, this is the goal of our study for this project. Okay, we want to have a comprehensive characterization on the aerobreakup of vaporizing micro droplets through high-fidelity simulation, right? We claim we do high-fidelity simulation. Of course, I do very careful comparison and validation against a high-fidelity experiment. And then after we get the simulation data, we want to develop data-driven machine learning models to predict the shade deformation, the drag, and the vaporization to enable accurate and efficient Lagrangian spray simulation. That's kind of the overall goal. We do not achieve all of them, but that's where we head into. Okay, so the first part, let's talk about the micro jobs. So the setup is very simple. You have a cube in the Basilisk, just a cube domain. You put a droplet at the center and near the left boundary a little bit. You have a uniform inflow in the flow on the droplet. These are the parameters. We try to pick the parameters consistent with the experiment by Jekyll and Asher grids. And here, there are mainly two physical parameters I change. One is the diameter. The other one is the diffusion velocity. So at the end, my Weber number changed from 12 to 24.4. I want to be careful not going to too ambitious Weber number at this point. And the diameter, I changed from 1.9 millimeter, and that's what they use in the experiment. So I started from a case, the millimeter job that's well documented, and then I move on to some micro jobs, 40 micron, 10 microns that they don't have experimental data to compare with. But we believe if we validate it with the millimeter job, I mean, it should be accurate enough for the micro job as well. So the simulation mainly done by my PhD student, Tavi Hassan Mahmoud. And you can see that when for the same Weber number 12, when the job is 1.9 millimeter, the Reynolds number is 2000 something, and they will decrease all the way to lower than 200 if I go to the 10 micron job, if I keep the Weber number unchanged. Okay, so just a general behavior. So to remind you how will this happen, you have a spherical job, it's posed to the free stream from the left to the right. The job will deform to a disc and later form a bag, and the bag will rupture by forming holes and eventually have the ring. If I wait long enough time, the ring will break into droplets as well. So this case, at the initial time, the job I have 512 cells. Okay, when the job deform and form into a bag, the liquid should become very thin. I gradually increase the resolution, the level refinement, until I equivalent to have like 2000 cells across the job diameter. Okay, so this is, at that time, is already the maximum I can push. If I go higher than that, the supercomputer people will complain with me all every day. With this kind of high resolution simulation results, we got to characterize the evolution of the job shape. We can truncate the overall process into multiple phases. Okay, so the green line here measure about the radius, the lateral radius of the droplet. So they kind of increase monotonic in time. But if you look at the time derivative, look like the lateral velocity of the job edge, you can find out they will increase such a plateau, increase again, and decrease the plateau and increase again. And that helped me to truncate the overall process in different phases. The first phase, when the lateral velocity increases, when the job from a sphere remains more or less as ellipsoidal kind of shape deformation. Okay, and the second phase, when suddenly the velocity increase again, is when the job from ellipsoidal now turn into a disk. Okay, and then you find out that even the radius continue to increase in time, the velocity increase of velocity actually decrease. And that's when this is deforming. Okay, that this did not expanding so fast. It's just more or less maintained. It's still expanding, but low velocity because it's just changing its shape, the center getting thin. Okay, and then you have a plateau, the velocity is kind of constant increase, is when the thin region at the center start to curve downstream and start to form in a bag. And in the phase 5 here, in the bag, it starts to inflate like a balloon. Right? If you play with bubble gum, you blow the bubble up, and eventually, of course, the bubble will break. Right? The thin liquid sheet here, I did not show it, but the bag rupture phase is the last phase. So we carefully compare our simulation results with experiment. So all the symbols here are the experiment of the job length. So I measure X minimum position and maximum position. The difference is the length. The Y maximum and the Y minimum is give me the diameter. So this is the length, that is the lateral radius or diameter. And you can see that our 3D simulation results, okay, the red dashed lines, agree reasonable well with the experiment. And you look at the experiment data, they have also some dispersion with each other. Okay, so there's some uncertainty in experiment data as well. With this kind of level of agreement, we believe the simulation capture the dynamics of the bag formation in the early stage of inflation very well. So I talk about the high computational cost of the 3D simulation. If you'll be able to do it in 2D, it will be much cheaper. And that's where we started. So you can see this, the two lines here are the 2D simulation. I can go to even higher resolution. I can get converged results, but they converge something different from the experiment. Okay, and for the job length and for the job radius as well. If you look at the velocity job, you'll find out that the 2D results even deviate more from the 3D simulation. And of course, the velocity is different. You look at the drag coefficient, you'll see the 2D simulation even further away from the 3D simulations. So I want to convince you is that the 3D simulation is necessary for this kind of case. Yes, Jacob. 2D asymmetric. Yeah, okay. So, I mean, you may ask why, right? I mean, the shape of the job look here quite 2D asymmetric. Why 2D asymmetric simulation cannot cut it? I mean, then if you just plot the vertical structure of the flow behind the job, you'll see. I mean, you have a turbulent wake developing along the process. If you don't resolve the turbulent wake well, you don't get the right pressure field, and then you're not going to get the right shape of the job. If the drag is changing and acceleration changing, interfacial dynamic related to the acceleration will change as well. So, I mean, I know this is an expensive game, but this is necessary to play. I mean, unless we will have be able to develop a turbulence model so that we can, in a 2D simulation, to account for this kind of effect. Otherwise, this will be necessary. So, I picked the paper, Stefan. Definitely, I believe when for Hansen, you work on this, you get converged result in the 2D. But if you look at the shape of the droplet for that Weber number, they still have some difference compared to the full 3D simulation. And I do believe this is related to the turbulent wake downstream, because you look at the pressure field for the 2D asymmetric simulation and 3D simulation, they're very different. If a 2D asymmetric, you always have a nice vortex ring over there, so the low pressure region is a certain angle with respect to my job. But in the 3D case, when the turbulent wake, no, the pressure is much more uniform downstream. Of course, they will influence the job shape evolution. In our case table, I can pick cases with the same diameter of the droplet, but vary the friction velocity so that I can vary the Weber number. So you can say, you can see that when Weber number is small, the drop does not break. They will deform toward this, but eventually they will retract back to the droplet. But if you increase Weber number, you form a bag, and if you increase Weber number even more, you see a stem forming at the center. So you can change it from the no breakup to the back breakup mode to the back stem breakup mode by changing the Weber number. But this is well known in the literature. We just show that we recover this this kind of transition in different modes by changing the Weber number. What really the new contribution from our work is that if I keep the Weber number the same, but I change the diameter of the droplet, what will happen? You find out that for a millimeter job, they will break like a bag. But if you go to a 10 micron job, same Weber number, then now it becomes stable. Okay, if intermediate 40 micron jobs, they form a tiny bag at the center. Eventually get pieced through, but they don't atomize and form thousands of trillion droplets from the back rupture. Okay, so this is just a snapshot of the 3 cases I've shown. If you have a millimeter job, the job will form a bag and eventually form some hole over there and expand and break. And for the second one here is the 40 micron jobs. They will form a tiny bag here, and the breakup of the whole, the bag is less wide. And for the last case, the 10 micron jobs, it becomes stable. So if you look at the first 3 phases, ellipsoidal deformation, a disformation, and this deformation, the 3 cases, they are quite similar. All the magic happened about in phase 4 when the bag started to form. Okay, and then the job size seemed to matter. with the same Weber number. Okay, if you remember, the Weber number characterizes the gas flow inertia compared to surface tension, that ratio is constant. Okay, so what changed? So when I look at my table, these two cases, one is unstable, barely unstable. 1C is the one is stable, the 10 micron job, okay? And same Weber number. Then I find out that when I change the diameter of droplet, two-dimensional parameter change. One is the Reynolds number decrease. Second is the Ohnesorge number increase, right? So when Ohnesorge number increase, that means the viscosity effect become more important. It can stabilize the job. And Reynolds number, we don't know. When the gas Reynolds number decreases, how will that change the job deformation? No. So, and then because these two happen at the same time, I do want to look at the individual effect. So we do a numerical experiment, right? In a real experiment, it's hard to do it, but in simulation, we can do that. So I hold the Reynolds number, and I just increase the Ohnesorge number, and I find out that the job from breakup now become non-breakup. Okay, so two, when I increase the Ohnesorge number by self, keep the Reynolds number unchanged, I'll be able to stabilize the breakup. And another game I can play is I keep the Ohnesorge number the same, just reduce the Reynolds number. And interestingly, I also find out that the job is stable. Okay, so reducing the diameter of the droplet, I introduce a decrease in Reynolds number and increase Ohnesorge number. Both of these two changes contribute to stabilize job breakup. Which one is more important, right? So we put all of those together. So keep in mind the red line is the 40 micron job that will break, and the blue line is the 1C is the 10 micron job that's not break. And this is the case that I only increase the Ohnesorge number, that's a green line. And I look at it quite similar to the 1B, but less similar to the 1C. And the purple, the magenta line here, is a case that I just decrease the Reynolds number to keep the Ohnesorge number unchanged. And you find out that the job shape change more when I reduce the Reynolds number than increase Ohnesorge number. I think probably because here for this case, the Ohnesorge number is reasonably small. It's in the order of 10 to negative 2. So even though increase them 2 times, it will increase some stabilization effect, but it's not the most dominant one. We found out the Reynolds number is more significant. Just by reducing the size, reducing the Reynolds number, it has a bigger impact on the job deformation. When you change the Reynolds number, the job, we know that the very classic Jack correlation, right? The Jack coefficient depends on Reynolds number. When you reduce Reynolds number, your Jack coefficient increase. And for a long time, people think about back breakup is driven by Rayleigh-Taylor instability. And that's understandable. If you have the gas flow accelerating from left to right, you have the job over here turn into a disk. So on the windward surface, you have a gas accelerate into the liquid, and then we know that Rayleigh-Taylor is going to be unstable. And on the downstream side, the leeward side, you decelerating, I mean, so you're going to have a stable Rayleigh-Taylor. So people think the baroclinic torque are going to contribute to deform, make the windward surface unstable, so your windward pole going to move faster and penetrate into the back and form in the back, and that has been believed for a long time. Now, if I change my job diameter here, my Reynolds number change in order of magnitude, and from 2000 to 200, the Jack will change quite significantly, okay? But we look at the windward surface, there's a solid line with the 3 different colors. We look at the windward pole position, velocity, evolution over time, we don't see any difference, okay? So if we continue to measure the thickness of the back and look at how they evolve over time, in early time, the 3 diameter of 3 different Reynolds number cases, they almost the same. When you have the small droplet, lower Reynolds number, higher Jack, high acceleration, instead of make it more unstable, they make it more stable. Okay, so that the thickness of the job decrease at some point and then increase back, but it oscillate back to they did not break, did not form a back, did not inflate at all. if you measure the length of the bag, so here I look at the distance between the minimum position and the center of the remote pole, that what we call the bag length. And if the job is not the concave shape, it will be 0. So whenever it becomes non-zero is when you start to see a bag forming. In the formation time, the small droplet, the low Reynolds number hijack case happened later. Okay, so that seems to tell us that even decreasing Reynolds number enhanced jack and enhanced RTI, but RTI actually does not really have big impact in the early time deformation of the job and the back formation. Then what really happened? What Reynolds number changed so that the back moved from unstable to stable? We believe that's really related to the wake again. So when you go from 2000 Reynolds number, you have turbulent wake, and to 10 micron, you have a couple hundred Reynolds number. Your pressure coefficient on the surface of the job will change quite dramatically. And that change of the in the pressure field for the low Reynolds number case, long story short, we're trying to bend the droplet like the blue curve here. They will make it curve in the opposite way that we eventually form the bag. Okay, so eventually the bag can form if the Weber number is high enough, but because the deformation of the disc now is in the opposite direction of the bag shape, it will take some more inertia, a higher Weber number for the bag to really be able to form and inflate. And we believe that's the key reason. And of course, if you work harder and simulate more cases, and this is a regime map we obtained. So the x-axis is the Weber number, the y-axis is the diameter. So increase in diameter will increase Reynolds number as well. We found out that if the left bottom corner here, low Reynolds number, no Weber number, no breakup, and then you have some kind of incline, a boundary regime, a boundary change from the no breakup to back breakup, breakup to the back stem. Okay, so if you think about this, tells me about the critical Weber number for the mode transition to happen. That Weber number will increase when the job size decrease from millimeter job to micro jobs. Okay, I mean they don't increase the order magnitude, but reasonably significant, like 20–30% of Weber number, right? So for the millimeter job, well documented about 11 Weber number, the back breakup will start to happen. But if you go to 10 micron job, you need to go to 15 or even higher for you to see the back breakup. And for the back stem, you just need to go to a little bit over 15 for the millimeter job to see the back stem happen. But for the micron job, 10 micron jobs, you need to go to almost like 20. Okay, so this is just a summary for the first part. And we look at the job size effect, and it will reduce the job size, we decrease Reynolds number, increase Ohnesorge number. We believe the Reynolds number is more important, and that's because it moderates the flow field and the pressure field, and that hinder back development and also the job breakup and also the mode transition. Okay, so I need to quickly move on to the next part, look at the phase change. Okay, so if we want to study phase change and we look at a case that is more like a boiling, the phase change driven by temperature. Right, so we need to solve additional equation for the temperature field, the gas temperature and liquid temperature. And based on the temperature, we calculate the gradient, we calculate what the heat flux difference on both sides. And if heat flux is not balanced with each other, you're going to have a source that drive phase change. You change your continuity equation, also your Wolff advection equation. Okay, my former postdoc Bradley, he managed to develop a method that handle this, because if you calculate the source term and you apply on the interfacial cell and you're going to contaminate the velocity field, the direction of the interface is not going to be correct. So one trick we find out that is that, okay, so I find out the source, I find out temperature gradient carefully, not taking gradient across the interface, and after I find the temperature gradient, I calculate source term, I do not apply immediately on the interfacial cell. I apply to the neighboring gas and pure liquid cell to avoid contaminating the velocity of the interfacial cell, and we call this like a distribution source method. You're going to kind of thicken the interface in somewhat, but it's a very compact kind of thickness of the interface. And we do tons of tests and make sure this really give us to the right solution. So one test case is a bubble, right? So it is a vapor bubble and it's driven by phase change and going to glow in time. And we can compare the theory. So this is bubble radius increase over time. You can see if the bubble vaporization happen, the gas now turn into the liquid gas, the liquid now turn into vapor. The density change will create a Stefan flow. So even though you look like the bubble just slowly grow, I mean, but actually generally the flow is much faster than the growth rate. Okay. So then we apply the code to simulate vaporization of a spherical job. Now let's do not worry about the flow, just a job sitting over there and vaporizing. And there is a good empirical correlation of data to compare with. Now the problem depends on the Stefan number, the Prandtl number, and the Reynolds number. And the typical model will characterize the vaporization rate by the Newton number. So they have come up with the Newton number correlation. If you don't have phase change, this is the Rance-Marshall law, depends on Reynolds number and Prandtl number. You have a vaporization, you have a correction, the Stefan number. Okay, and we do the simulation, no flow, and to compare with it, and you can see we very different liquid and vary the Stefan number, and we compare the experiment, we get reasonable agreement with the experiment. And then we go back to our case. Now you have aerodynamic deformation of the breakup with the job. At the same time, vaporization happen. On the left figure here, we show the volume change rate. How does the vaporization happen? The job going to decrease in time, but we look at the rate, the vaporization rate. And on the right, the red curve is the surface area. So you can see these two quantities, they're very well correlated. So the job deformation, increased surface area, you're going to have faster vaporization. The job going to lose its volume faster. Okay. More interesting is that, again, same game I play. I keep everything the same density ratio, same Weber number. I just change the Stefan number. I want to see what happened to my joblet. So for the case without vaporization, the job will get pieced through, break up, and forming joblet, small joblets. But when I put Stefan number equal to 2, then I have vaporization. Now the job becomes stable. They don't break at all. So if we consider the minimum Weber number that required for breakup to happen, we call this critical Weber number, you find out that it will increase with Stefan number. Okay, and this is true for 3 different density ratio. This is a bit like a liquid acetone, and the large 700 is like water. So you change the liquid density to gas density ratio a bit, but this is quite robust conclusion. Okay, so if you have a stronger vaporization happening, your job going to require a bigger Weber number, a bigger inertia to break it. Okay, of course we try to understand what happened. If you have vaporization happen, there's 2 things happen to my job. One is that my job going to decrease in volume, so the interface will move toward, recede to the liquid side, okay? And second is that when the liquid turn into vapor, you have a lot of volume going to generate it, they going to generate a Stefan flow. So these 2 mechanisms, who contribute more to the stabilization of my job, right? Again, that's the advantage of doing simulation. I can force my code to only do one thing at a time. So the black line is that no vaporization, so no Stefan flow, no interface receding, volume constant, thanks to the Wolf method. And the red line here is that, okay, I allow the job size to reduce based on vaporization, but I suppress the Stefan flow. I turn off the source term in my flow field. And the third case is that I just allow the phase, the change to generate Stefan flow, but I do not allow my job volume to change. No interface receding. And finally, the green line is both mechanisms happen, the full simulation for vaporization. And you look at the 3 different density ratio. Very easily, you look at the blue line, agree with the red line much better. And the red and the, okay, so the red and the black are quite similar. So that means interface receding does not really help to stabilize the job. The job supposed to break, it will still break. But for the case that I turn on a Stefan flow, even no change in the volume, without changing the volume of the joblet, we see the stabilization of the job. So my conclusion is that the Stefan flow generated by vaporization is the reason for the job to be stable. And we look at the case, the flow field. If you have the Stefan flow, you have the vaporization, 7 number equal to 2, you look at the job shape, and they are slightly different. Okay, the main difference is that now the job tilted more inclined to the right. Again, this is shaped against the back formation. Okay, and why this happened is when the vaporization happened, they will moderate the boundary layer near the flow separation point, and they push the wake to a little bit higher. And the change of the flow field now influence the job deformation. Okay, and when this change of the flow field, the pressure field, they also will, I mean, you can understand the pressure difference is mainly changing the jack. So vaporizing also will enhance the jack. You look at the jack coefficient for this 3 different Stefan number, you see that for the Stefan number equal to 2, the cases, for example, most of the time, you get almost like a double the jack for the case without vaporization happening. Okay, so by looking at the vaporization, we find out that there's an interesting interaction between the two, the deformation and the vaporization. And across a wide range of density ratio, if you have vaporization, you need to increase your Weber number to break the job. And that's quite robust conclusion. And we find out that the asymmetric Stefan flow modify the pressure field, and that's the reason for enhance the jack and also suppress the back formation and development. Okay, with very little bit time, I want to quickly talk about, let's say, if you trust those simulations I have done, how are we going to use it? Right? Each of those cases take 2,000 CPU for weeks, right? But how will people use this in the case that they have 1 million of jobless? For those cases, you need models, right? So we're trying to develop data-driven model. So a long story short, here I first look at 2D asymmetric simulation for low Reynolds number, low Weber number case. So the job here will not break, they will oscillate. For develop data-driven model, now you do many cases, right? You need to find some way to define your parameter space, and you find some way to fill with like 100 cases. Okay, so with the data here, you need to truncate them into training set, validation set, and the test set. So for this case, we have run like 100 cases. So I can get everything, but the model does not want everything. If you have played with the neural net, you find out that a model, if you have a lot of data input, a lot of parameters, the model will become very complicated. So we want to find a way to characterize the shape of the job in a way that can reduce the number of input parameters. So one way we have found out to do it is do the spherical harmonic decomposition. Right? I don't want to have the coordinate of all the individual points to define my shape. I would try to decompose them into spherical harmonic mode. So, and then, you know, the mode coefficient generally decrease with the mode number. So I can truncate like a 10 modes, and with the 10 mode coefficient, that will be enough for me to characterize the shape of the job. And the time evolution of those mode coefficients is what I'm going to send to my neural net. Okay, so I take the history of C0 to C10, 10 spherical harmonic mode coefficient, and send it with the Weber number, Reynolds number, the flow parameters to a neural network, the multi-layer perceptron. This is a simple deep neural net, and to predict the future mode coefficient. Okay, so from n minus lag, the history steps, to predict n plus 1 to the n plus s, the stride, okay, the future. And after predict the future, you feed it back to the history and predict the future. So eventually, the model is fully recurrent. Okay, if you tell me the starting point, initial condition, I will kind of predict myself, and based on the prediction, I go to next prediction, next prediction. And I will quickly some details. So when you train the model, you do open loop. So you do the history, send it to network, do the prediction, you compare with the ground truth, the simulation data, and the difference gives you the loss function. Okay, and you do many different history, period of history to predict and sum the loss, and that's what you want to minimize to tune the parameters, parameters of neural net, so that your model is well trained. And after you train the model, the prediction is closed loop. Okay, so we don't rely on the simulation data anymore. From the starting point, you do the prediction, and the prediction now will become updated inputs to the model to do the next prediction. Okay, and we do the same thing for the similar things for the drop shape and for the drag, and these are the parameters we have used in the model. And you can see the model do a very good job in predicting the mole coefficient. So this is second mole coefficient, third mole, fourth mole, and fifth mole, and you almost cannot see a difference between the prediction and the simulation data. That means the model is doing a very good job. And this is with the mole coefficient, I can reconstruct the drop shape and how it evolves in time, and you can see the prediction and simulation data also match very well. Okay, so this summarizes the data. So for training, for the diameter or for the shape of the droplet, we get less than 1% error, and for the drag, it's a little bit over 1. In general, the error will increase with the Weber number, but for all the cases we have tested, we have the error less than 2%. Okay, so I will not have time to talk about that, but that's the easy case. The job is have a mild deformation. If job going to deform significantly, then it is, you don't know what does it mean for spherical harmonics, right? For this case, you cannot even define the radius of function of theta. And for this case, there's an additional mapping we need to do, right? You can have an arbitrary shape, but you map it back to the circle to define a new coordinate theta. And after you do the mapping, you do the spherical harmonic transform, you still use the mole coefficient for the new map geometry to train the model. And we have some good data to results for this case as well. Just today do not have time to talk about it. So the summary for the model prediction is that if you have simulation data, you do want to try if there's some way to model it, right? And your model physics approach is kind of limited in the way that we can push. So machine learning gives us a new way to do data-driven models, but that's not something that you naively throw all the simulation data you have into the model. That would be a disaster. So we found out that you need to be carefully to do the shape characterization, reduce number of inputs, and then we have tried to use a recurrent neural network to predict the drop deformation and drag, and we get pretty good agreement. Yeah. So to continue, for the future work, we want to look at the combined effect, Reynolds number and Stefan number add together. How would that change the breakup time, breakup outcome, the drop statistics? And we want to see if we can push to higher Weber number that the drop will deform in the backstem and multi-back mode. Okay. Now we look at a case, the uniform flow. What happens if the flow is not uniform? How would that complicate the process and compressibility effect, and eventually go to like a droplet-droplet interaction? Okay. So yeah, so I would like to stop here. Thank you for attention. There's some papers related to the work that I have talked about, and if you're interested, I definitely would love to talk more about that with you. Thank you.
Thank you for being right on time. Yes, I didn't mention Stanley staying until Monday morning, but we'll ask him a lot of questions.
Yes,
so
please.
who has questions? Yes, Quentin.
Thanks a lot for the presentation. That was really, really great and really interesting. I think your conclusions on the effect of vaporization are really good for people that are doing sprays, especially spray flames, because it means that they do not have to change the models. So I think they would be really happy about that. So yeah, you kind of talked about it in your conclusion. What do you expect a lot of changes if you add a lot of turbulence, for example, in your flow? Mm-hmm. And yeah, can you give some insights about that?
Oh, yes. So right now you look at the cases we study, the stream coming is super clean, no turbulence. If a turbulence already coming over there, how would that change the dynamics? I do think that will have some effect, right? Because when we look at the cases, in particular, those that really on the fence can be stable or can be unstable, change a little bit on the pressure field, change the initial deformation of the droplet, that can have a big effect. If you have the turbulence coming in, you're going to change the pressure field as well. Okay, so I do believe that will have some effect, and we're studying that as well. Yeah.
So, I had a question regarding, at one point you discussed the relative effect of the gas Reynolds number compared to the Ohnesorge number in terms of stabilization. And I was wondering, is it a question of scale, and that's correct at 10 microns, or is it independent of the scale of the bubble size, this relative effect of?
Yeah, I do believe that's mainly the Reynolds number effect, right? I mean, Reynolds number not only depends on the size, you can change it by changing the viscosity, changing turbulence, we change the effective viscosity as well, right? That can also change the Reynolds number. And originally, we just want to look at the size effect, but actually I look at the parameters behind the size, there's Reynolds number and Ohnesorge number, okay? What the conclusion here is that for a low viscosity liquid, like water, Ohnesorge number, even for a micron drop, is still relatively small. Okay, so the Reynolds number seems to be more profound in terms of stabilizing the case. But if you have other cases, you have a high Ohnesorge number, you just have the two bad guys work together, then you probably even higher Weber number for the drop to become unstable.
One last question about you showed a the model for the drag coefficient with machine learning. So is that you used your machine learning model to predict the shape, and then you use a correlation for the drag, or you're also using another machine learning model for the drag?
Yes, sorry, I ran out of time, so I went a little bit fast over there. So it's also machine learning. Using machine learning model, very similar architecture to predict the shape and to predict the drag. But I don't use the drag to predict the shape. So the shape will only look at the spherical harmonic mode coefficient history. After I get the mode coefficient, they will together go to the drag together predict the drag. I mean, the shape, of course, will relate to the drag, right? And if the drag is also a transient process, so we also use a recurrent neural network to predict the drag. But I mean, we have some very recent results. I mean, almost something I got last week. We found out that if we do not take the history of the drag, just take the mode coefficient and the Reynolds number, we get reasonable prediction of the drag as well. Okay, so that means like, yes, the drop is deforming, but the history effect is not really important to the drag. The drag mainly depends on the Reynolds number is the instantaneous shape. But of course, you need to predict the shape, that you still need the recurrent neural net. Yeah. Yes.
The history of the drag coefficient that is not input for the future mode.
Yeah, not for the mode. For the shape, I don't look at the drag. I only look at the Reynolds number, Weber number, and the history of the mode to predict the future mode coefficient. Right, but for the drag, then I will use the mode and also the history of the drag to predict the future drag. Yeah.
So thank you, Stanley, a great presentation. I have a question regarding the 2D axisymmetric approximation, because you were always relating that to the turbulent wake, but then in fact you have the atomization aspect of the whole formation expansion dynamics, so you lose the symmetry in that event.
Oh yes,
that
yes,
usually
yes.
is one of the responsible steps.
If you have the whole forming, then 2D symmetric is wrong every point, right? But a lot of people believe that before breakup happened, my back shape still can be predicted well with 2D asymmetric simulation. It's probably not true for the high Reynolds number case, at least. Okay, I mean, even for our case with like a 200 Reynolds number, the wake is not nice and asymmetric. Okay, they will still have some shedding, and that will also deform the job as well. So it's really need to somehow in a 3D simulation to capture the right dynamics.
Okay, so maybe I lost it, but with the micro droplets, so what is the range in Reynolds that you get?
It's about 200 to 400. Yeah, 200 to 400. Okay.
Thanks.
So I mean, I do try to push to a very small droplet. Okay, if you look at something like 100 microns, something probably they behave quite similar to the millimeter drop. Okay, and you need to change the diameter a lot to see this kind of effect, right? So I mean, I do not want to oversell the finding, right? But there's some cases really you can have 10 micron, 40 micron drops in the engine that is breaking. Yeah. Yes.
So yeah, because I'm interested in stuff that burns, my question would be, do you think you could do these kind of simulations with droplets of kerosene, for example, which has the specificity of being multi-component? So basically, what would happen if you have the composition of the droplets that changes over time, and also you change the composition of the surrounding vapor?
Right. Yeah, I see your point. We did not get a chance to look at the multi-component. I do believe in the Basilisk user. There's another user of Basilisk. They deal with the multi-component vaporization. Here we just want to pick I am interested in the fundamental physics. Okay, so I need to admit that I'm not so follow my combustion colleagues so well. There's no field is a single component, right? You have multi-component, different vapor pressure. Some vaporize faster than the other one. Then how would that? What step number you're talking about? I agree. I mean, then there will be some. If you think about here, I look at the case. Everybody vaporize the same way. Now you have something vaporize less than the other one, then you will weaken the effect, right? So what I saw here is like a strongest effect, like the upper bound, right? You see something like a little bit lower than the upper bound. You can simply think about that.
Thanks.
I don't know, can you go back to one of your first slides where you had maybe shock droplet interactions?
No.
Yes. So, and maybe you had a slide before that, slide 2, which also had some. No, that was not slide 2. Maybe slide 3. Yes, drop impact on high-speed flight.
Oh, okay.
So this problem is very interesting. We studied it before the paper, in parallel with the paper with Florence Marcotte. We studied it with Timea Kekesi, and there was a lot of similarity between Timea's work and Florence's work. And in that case, the Weber number we estimated somewhere between 1,000 and 10,000. So do you think this is doable with DNS?
I feel it's very difficult. Yeah, that's why I never go into that regime. I think it would be very difficult with such a high Weber number.
I think we are beginning to see some work. There was some work by Theophanous and some work around Weber 1000. I'm not sure we can go much higher.
For experiment, I mean, they're happy to do more than 1,000, right? I mean, whenever they have a shock tube, they put a job over there, hit it by a shock.
They can numerically, yes. Can we go higher than 1,000 numerically?
Yeah, right. So
my rough estimate is that we need a number of grid points, or a given number of grid points of the order of the Weber number.
Right,
so
right.
10,000 grid points, we could do but I'm not so sure because the Reynolds number is also larger. So
yes. I mean, Tim
I wanted
Colonius
to know whether you had an opinion on that.
Right. I mean, Tim Colonius also did a simulation with the high Weber number case breakup, and there he even threw the viscosity away, just do inviscid simulation, right? And that would be very demanding in mass resolution, in my opinion. But But it's just probably the method also need to be evolved a little bit to be able to do a realistic simulation for that case. Yeah.
Okay, I have no further questions. No one has further questions, Stefan?
Just waiting to be the last one.
Thank you very much for the nice seminar. You showed a nice stabilization by the Stefan flow for the breakup. Do you have any evidence in experiments? Are there experiments which show the stabilization or?
No.
No.
I try to convince my experiment collaborator to do it for me, but so far not yet. Okay.
So your explanation is that it changes in effect the large scale flow and so the drag, so the pressure distribution on the drop, right?
Yes.
Is there a more local, could there be a more local effect, like the fact that because of the Stefan flow, locally you could generate, for example, in effect an associated pressure within the film, which will prevent it from draining in effect.
So I agree. So we have the Stefan flow, you kind of push the interface to the other way, right? Yes. I think so. I think that's definitely.
It's a bit like, it's the Leidenfrost effect, if you associate it.
Yes. Right. So I think the Stefan flow changed two things. One is locally pushing the flow. That's why I'm sorry, I went a little bit fast. If you look at the Stefan paper we published, we talk more details about that. The vaporization rate on the two sides of the droplet are different. So on the windward side, you have thinner boundary layer, stronger vaporization, so you get a stronger push. And the downstream, you have a thicker, you have flow separation, a weaker push. So at the end, the drop kind of tune this way. That against the back deformation. I do believe that. And then secondly, the Stefan flow modify the boundary layer and the flow separation. Then you have some global effect change of the pressure field and the drag change and so on. Yeah. I mean, it's quite interesting. Even though like a little bit touch, but they change the drag quite significantly.
Are there any questions online? Did you see? Yes? Okay.
We have a question. Have you ever experienced any issue with the expression term of phase change during breakup droplet interaction?
Can you repeat the question?
Any issues with the expression term of phase change? I'm not sure. Can I see?
Maybe you can translate for me.
Eduardo Cipriano. Yes. The expansion term is this term, divergence of U equals the source term.
Oh, yes.
And do you have any difficulties with this term when you do breakup simulations?
I mean, we need to have improved the method a little bit, right? The source term, I do not apply it right at the interface, all right? I put it to the neighbor of the interface, and that isn't necessarily get the right advection. Right. I mean, if you have strong vaporization, you need to control your time step to respect the source term, and that's kind of standard things we need to do. Yeah.
And Eduardo is also asking, is the boiling model, I suppose that's the boiling model that you are using, sufficiently accurate, or do you need to also introduce concentration-driven phase change?
Here we just look at the boiling case. Right, so the phase change is purely driven by heat transfer. I do not look at the concentration gradient driven. I don't look at evaporation. I just look at a strong vaporization case by boiling. Yeah.
Okay, so Eduardo, if you still hear us, are you happy with the answers? I don't know. Eduardo is not writing anything. But there is a delay, no? There is a delay, so maybe Eduardo has not heard us yet. Okay, Eduardo, I suggest you send either Stanley or me an email after you read of this. No, he says thanks a lot. Okay. Okay, so with this successful online interaction after the seminar, which is, I must say, it's quite rare, so it's quite nice. Well, let's congratulate Stanley again for his talk.
Thank you. Thank you.